Alright, in this video we're going to talk about some applications of MaxFlow and MinCut. So in this problem, we are considering some rail network. So we have a bunch of railroads connecting stations, and it's undirected because you can move from one station to the other and vice versa on the same train. And the question in this problem is you want to find a way to destroy stations so that you cannot go from S to T. So that's the goal of this problem. So just from that, it sounds almost identical to the MinCut problem, because in the original MinCut problem, the motivation was to literally destroy railroads so that you couldn't get from the one city to the other. So it's basically MinCut, but there's a few differences. So the first thing is it's an undirected graph. It's not directed. That won't be a huge deal though. And the second problem is we're removing nodes here, not edges. So in the original MinCut problem, the idea was you pick a cut, which basically is equivalent to choosing edges to remove. So a cut ST induces a set of edges that go between S and T, and you can think of removing those edges. But here, we're removing nodes, not edges, so it's not exactly a cut like before. So how can we solve this problem? Well, there's a very famous theorem from graph theory called Menger's theorem, which says the minimum number of vertices you need to remove to disconnect S and T in the graph is equal to the maximum number of node-disjoint S to T paths. So if you just took a bunch of paths from S to T that didn't share any nodes, and if you found the maximal such set, then that number, the size of that set, is equal to the answer we want. So this is the key thing we'll be using, but maybe you don't know a lot of graph theory, so you didn't know about this, so how can we actually do this directly using flows? So once we have Menger's theorem, what do we have to do? Well, assuming we have this, then the alg is just computes the max number of node disjoint paths in the graph in a graph G prime. Now, computing the number of node disjoint paths, we already know how to do this through MaxFlow, so we can just take that as a black box. We're going to reduce to that problem. But what graph should we be using? So how do we make it undirected? Or how do we make it directed? So to make G directed, there's two options. So the first option that we've seen in class is just for any edge U to V, we replace it with two edges, U to V and V to U. So that's one easy strategy. Just turn every edge into two edges that go in opposite directions. And ultimately, that's what we're going to do. It's very straightforward. It's not very complicated. But there's a more intuitive thing that we could do, which is we could run BFS starting at S to compute shortest path distances. So D of V for all V. And then what we could do is say U to V becomes the edge U to V if D of U is less than D of V. So intuitively, this is saying if our edge goes from a early vertex closer to S to a farther one, then we direct it from left to right. So the idea is direct everything away from S. So otherwise, it's V to U. So the idea here is direct edges left to right. I even spelt it from left to right. From S. So that's kind of the more intuitive thing we might want to do. We just make all the edges go closer and closer. As they get closer to T, they face that direction. Now the reason why we're not going to do this, we're going to prefer this one, is because although this sounds nice, it generally gets complicated and confusing how to do this when you have cycles in your graph. So things could go wrong. They won't necessarily go wrong, so sometimes this does work. So sometimes this works, but you need to prove it carefully, or at least think about it. So to avoid it getting complicated in any way, we'll just go for the straightforward way. So in G prime, we'll have both edges for a given undirected thing. And then to make it a flow network, we also need to add capacities. So for each edge, the capacity of the edge is going to be infinity because we really don't care about edges. We just want to find nodes. And then for each node, we will have the capacity of the node is 1. And that's just because we're doing a reduction to node-disjoint paths. Okay? So really, these parts could even be built into the node-disjoint algorithm, but just to be precise, I'm spelling out exactly what the graph's going to look like. So really, we could have just made G prime from step 1, where we direct everything, and then we're pretty much done. But internally, that's what's going to be happening. So now once we have that, we have this graph, we can compute the number of node-disjoint edges, or node-disjoint paths on it, and just output the number. That's the whole algorithm. So since we know we can build up node-disjoint paths, we can do that algorithm efficiently. Then the total runtime of this, obviously creating G prime is linear time. All we do is direct edges in both directions, and then we just feed it into the black box. So overall, it's going to take time O of V E prime, but E prime's the same size as E, we just doubled it, so this is O of E times E time. Okay. So given Menger's theorem, it's clear how to do this, but obviously we need to prove this is actually correct. In fact, by looking at the flow network, looking at the actual reductions we're using, will help us do this. So we'll actually get a proof of Menger's theorem by using flows. So the first thing we need to prove is the easy part. So let's suppose we had a bunch of disjoint paths. We're going to prove that the max flow is at least that. Or in other words, we want to prove the min cut is at least that. So let me rephrase this differently. We want to prove that the min cut, the min node cut, is at least the number of node disjoint paths So why is this? Well, just assume you had a bunch of node disjoint paths. So it looks something like this. you just have a bunch of these paths that don't reuse nodes and go to T. So because they're node disjoint, none of them share any paths. So each node appears in at most one path. And so if we wanted to disconnect S from T, at the very least, we would have to kill one node per path. Because if we missed even a single path, then that's one path that we could still take. So in particular, let's say we didn't kill this node here. Well, obviously S and T aren't disconnected. We can just take this path here. And that gives us a path from S to T. So at the very least, we have to touch one node per path. So need to delete at least one node per path. And so that proves the claim. The min node cut size is at least the number of node disjoint paths. So that proves the first part. Now we also need to show that the number of node disjoint paths is sufficient. So it's clear that we have to kill at least that many nodes, but how do we know that that's enough? Maybe we kill that many and there's still other nodes that need to be killed. And this is the hard part. So is the number, so let me keep calling it NDP, sufficient to disconnect the graph? And the answer is yes. In other words, that MNC is at most NDP. And this is the key part of Menger's theorem. It uses induction, but here we're going to actually look at the flow that's created in the graph, and that will help us. So let's actually look into the reduction, what it's actually doing. So remember, when we do this reduction to node disjoint paths or any kind of node capacity thing, we're really creating a V in and a V out for every node. And then we put a single edge there with its capacity. So this is the node capacity. And then everything else are the original edges in the graph, which for simplicity we made to make it to simulate undirectedness. We had both sides, but remember they're both infinite capacity, so it doesn't really matter. Those will never even have a chance of being taken in the first place. All right. So if we looked at this graph and we looked at the min cut in this graph, so we find some min cut, S to T, this is in our graph G prime. Well, what's really happening in here? So each edge that crosses the cut, notice each edge that crosses the cut has to be one of these V ins to a V out. And that's because if we tried anything else, if we had some like U out to W in, well, remember this has infinite capacity. So that would give us an infinite capacity cut, which is not optimal. Because obviously, in the very worst case, we could just choose every node in the cut, and clearly every node in the cut will disconnect S from T. So we always know the min cut is at most n minus 2, since could delete all nodes besides S and T. And I'm assuming here there's no edge from S to T or T to S, because obviously if you can just go straight to T from S, then it doesn't matter how many nodes you delete. Okay, so we know that these types of edges can't happen then because they're not optimal. So these are always edges from a V in to a V out. So really what this turns into is the capacity of the cut, because there's a single edge from V in to V out, and there's no other edges, right? The only edges from V in to V out are a single edge, and V in does not connect to any other nodes. So what this looks like is the capacity of this cut is equal to the number of nodes that we delete. So we have exactly one edge per V in, and so that corresponds to exactly one node V. Because remember, these edges always correspond to a single node by definition of the reduction. So any ST cut is really giving us a vertex cut. It tells us vertices we can delete. And so if we knew there existed a if there exists a number of node-disjoint paths, we can use that to create the min cut. And this is just from the max flow min cut theorem. So in particular, now using max flow min cut, we know that the capacity of the min cut, this is actually equal to the value of the max flow F star. And this value, by definition, is the number of node disjoint paths, the max number of them. And so ST, that gives us a specific cut. This gives us a specific way to delete things. And so the minimum node cut is at most that. So here we end up getting the fact that the minimum node cut is at most the number of node disjoint paths by using the max flow min cut theorem to relate them. And this is something you'll do all the time, and we'll see more examples of a little later. All right, so that gives us a proof of Menger's theorem. So to summarize, the first case we can just solve directly. We just see clearly that if we don't delete one node per path, that leaves us a path we can take. And so the min node cut size is at least the number of node disjoint paths. Then we figure out that, in fact, the number of node disjoint paths is sufficient. We can actually pick one node per path to kill, and that's enough, by appealing to the max flow min cut theorem. And specifically, we look at the flow graph in our reduction G prime, and we actually look at what the cut would mean. So if we had a max flow and we looked at the corresponding cut, the cut corresponds to a way to delete nodes. And so the best we could do is no worse than this, because this is one possible solution. But by max flow min cut, this is also equal to the number of node disjoint paths. And so that gives us the entire result. So this problem, which seems pretty similar to min cut, the original, we are able to essentially solve using min cut. But this version is actually a little more complicated than the original, and we have to do these two reduction steps to get it down to the number of node disjoint path problem, which is what we ultimately solve at the end.